Thank you for joining us this evening. You were brought into this session with microphone and video off. If you have questions, please put them in the chat. We will collect them and address them to Russ after his presentation. This program will be recorded and it will be made available on the Detroit Public Library YouTube channel and through Wayne State University's website. I am Jennifer Dye, a librarian at Detroit Public Library. We have offered astronomy programs for the last several years. When things fell apart in spring 2020, we put programs on hiatus. We finally launched the astronomy programs on Zoom early last year. And we feel that these have worked well. We have people from all over the world, which is very exciting. Over the last several months, I've been pleased that we're working with Megan McCullen, director of the Wayne State University Planetarium, in particular on programs presented by Wayne State faculty and alumni and other associates of the university, like Russ. We also work with members of local astronomy clubs. We look forward to looking with local groups and with Megan and the planetarium. Our September program is still being developed, but in October, Adrian Bradley will show us how to get good pictures of the moon. And in November, Sean Gavin will tell us about the knockdown, drag out controversy about whether Earth and the sun were really old enough for Darwin's theory of evolution to make sense. I'd like to ask Megan McCullen to speak briefly before I introduce tonight's speaker, Russ Carroll.
Thanks, Jennifer. Hello, everybody. We're always glad to have you here. And as Jennifer mentioned, we've been doing these for quite a while now. We're working on a lot of updates to the planetarium website at the moment. So give us a few weeks and we should have all of the videos up there along with information about our in-person events at the planetarium, which are going to start again this fall. We'll keep doing virtual programming as well, but we are going to start bringing back some in-person public shows on Friday nights, some K-12 groups coming in, and our Science Under the Dome lectures in person. So we'll have both options for people. So those should be great, but we're finalizing all of that right now. So stay tuned and we look forward to seeing you here and back on campus. And I think that's
Good
about
timing
all I've got for you, Jen.
Good timing as always. Sorry about that.
Sorry.
Thank you, Megan. Russ Carroll grew up in Rochester. His father was a senior engineer at the GM Tech Center in Warren. Russ became passionate about astronomy at the age of 11 when he and his older brother scratch-built an 8-inch reflector telescope, even hand polishing the mirror. During his sophomore year at Rochester High School, Russ started college at Oakland. In his mid-teens, when a photometry project hit a wall at Oakland, he was granted permission to use the observatories at MSU and Kitt Peak National Observatory to continue his research on binary stars. He subsequently went on to work at the Naval Research Laboratory and published one of the first discoveries of the new HEAO-1 X-ray Observatory at the age of 17. He was later on staff at the UCSD Center for Astrophysics and Space Science to further his research using the new Einstein X-ray Observatory and optical telescopes at Kitt Peak and Cerro Tololo, Chile. And I'm sorry if I butchered that. In his 20s, Russ went on to a career in supercomputing at Boeing and digital productions. DP produced groundbreaking computer graphics, including 22 minutes of CGI in the film The Last Starfighter, as well as hosting several engineering companies and the NSF in using its Cray supercomputers and specialized animation image recorders. Russ has founded or run multiple tech companies and is now semi-retired in San Diego. Russ designed, built, and donated the Dan Zowada Memorial Observatory at WSU, a fully robotic observatory in the high desert of New Mexico. Russ is a former board member of the Astronomical Society of the Pacific and a member of the American Astronomical Society. Russ, welcome. Thank you.
Thank you, Jennifer and Megan, and hi, everyone. When Jennifer and Megan approached me to give this presentation, I jumped at it because it included two of my very favorite things, and that is the universe and Michigan. So I'm very happy to be here, and I have a lot of material, and Jennifer told me I only have 2.5 hours to present it, so let's just jump right into it.
2.5 hours, I told you?
Oh, wait a minute, I'm getting a text from Jennifer. It says, I said 40 minutes, and even that sounds like a lot at this point. Okay, well, we'll make sure it's not 2.5 hours. I'll show you this. I'll be done in time to watch my Tigers play my Padres tonight, so we'll be out in about an hour. So my topic is really a broad topic, and I've taken license with it, as I typically do on subjects like this. But it's important because, for no other reason, I think the most important reason is the Webb Space Telescope is going to be in the headlines, and it's going to be really altering what we understand about the universe for the next several years. And it falls in an area that's not visible. It's taking images that aren't visible to the human eye. So it's very timely that this presentation is somewhat oriented towards that to a general audience in the house and the wise. But so this is from Wikipedia, true versus false color. An image is a true color. We call it true color if it's representative of what the human eye sees. If we take a picture with our iPhone or camera and it looks pretty much like what we photographed, that's what we would call true color. Now, false color is not that. It does not appear, for whatever reason, to look like what it would look like to the human eye. So, what are the primary reasons for using false color? Well, to better convey information or enhance detail, number one. So, in astronomy, the idea is to clarify, to push better information and understanding as to why we would use false color instead of true color. And the other reason is the one I mentioned earlier, is to show images that aren't visible in parts of the spectrum that the human eye can't see. So let's look at true color for a second. So light acts both as a wave as a particle, and we're going to be talking about wavelengths a lot and the wave nature of light. You can see here's a spectrum over here that shows the light is part of the electromagnetic spectrum that goes from very long wavelength radiation like radio waves through microwaves and infrared to the visible. You can see the wavelength, the peak to peak, getting smaller and smaller into the visible light, and then back to areas we can't see again in the short wavelengths like ultraviolet, X-ray, and gamma rays. And when you diffuse light, white light, you can see that white light is made up of different colors. And when we send it through a different medium like a prism, we see that dispersed. And the reason is different wavelengths refract at a different angle. And so up here you see the reds, and then down here the yellows and greens, and then finally into the blues and violets that make up the individual components of that white light. So the first astronomical detector that ever existed was a human eye and vision. Eye is, basically the lens of your eye is basically a telescope forming an image on the retina back here, which is essentially an image detector, an image sensor, sending signals through the wiring, which is the optic nerve to our brains, which are more or less an image processor. And, it's kind of an urban legend when I grew up that you only use 10% of your brain, which isn't true. Vision actually takes up a good deal of it, although my mom wondered if I even used that 10% when I was a kid growing up on a few devil's eyes that we had. But we do use a lot more of our brain than 10%, and vision takes up quite a lot of it. It's doing an awful lot. So there's photoreceptors in our retina that are like an image detector, like a CCD or a CMOS detector in your camera, in your iPhone or camera or what have you. It's made up of rods here, which are basically, they see light levels, black and white. So in very low light levels, we're using the rods within our eyes for vision, and that's why we don't see color. In brighter light, cones are used, and you can see that there are three different types. There's short wavelength ones here in the blue, medium wavelength cones in the green, and long wavelength cones in the red, which sense color. These are pigments. By the way, that I'm going to go back. There's, oops. I'll go back. This is impressive. There's 120 million of these rods and 7 million of these cones in each eye. I mean, that blows me away. You know, one of the things preparing this talk, I've studied astronomy and imaging my whole adult life, but I've never thought of how amazing the human eye is, and this is just one aspect of it. So here's kind of the spectral response of those, the rods in our eyes and the cones. Here's the spectrum and wavelength in nanometers, going from high 300s up to near 700, from violet to red. And here's each of the response, the absorption, essentially, of each of those cones. So here's the red at 564 nanometers, green cones here, the blue cones here, and these are the rods that are kind of our black and white vision. And these are sending signals to the brain. The amount of red, the amount of green, the amount of blue that any individual object is reflecting or emitting. And our brains are processing all that information to give us a sense of what the color of an object is. Here's a normal distribution of cones in the retina. Here you can see there are lots and lots of red. Red is the most common one that we have, and we have about 60% of the cones in our eye are red sensors. 30% of them are green, and only 10% of the cones in our eyes are blue. And on the right is somebody who is colorblind. What happens is there you can see you see a total absence of red pigmented cones, and so they don't have, people that are colorblind don't have the sense of color perception that we do. So here's a digital camera and how it handles color. This will be in your iPhone or your digital SLR. You've got the subject that you're photographing. You've got a telescope or a telephoto lens, which is forming an image on an image sensor. But before that, it's passing through a mosaic filter that covers each individual sensor that's measuring intensity. One thing you should know is all these image sensors, all of them, are not sensitive to color. They only register intensity. So they don't really have any basic information about color. And so we put a grid of red, green, and blue filters in front of them to be able to pass on that information to a computer that is going to convert it to a color image. So here you have your digital camera here. So there's the sensor in the camera. The sensor itself, which registers in light level or intensity at each pixel, has one of these filters in front of it. When you take a picture, that raw data gets passed off goes through a process called a debayering process that takes the grid of each of these, separates them out into red, green, and blue, interpolates what a complete red image, green image, and blue image looks like, and transmits them where it's reassembled, basically. So here's the reassembly process where you have a complete red image, complete green image, and a complete blue image merged together to create a natural color image. On the other side, on the image creation side, here's what a very close-up of an Apple Retina display looks like. it's kind of the reverse. It is emitters. Instead of receiving light, they're emitting light. And you can see it's just segments of red, green, and red, blue, and green pixels here. And so the red image emits the amount of red through the red dots, the green through the green, and the blue through the blue, so that when you pull back, you see what is a natural looking color image of something. Now, astronomy cameras are a bit different. Everything in professional astronomy is essentially done with monochrome sensors. This is what we use at the Wayne State Observatory. This is the exact equipment. This is a very sophisticated CCD element here. It's 4,000 by 4,000, I believe. Very, very light sensitive in a broad range of spectrum. And it sits here in a housing that brings it down to a very, very low temperature so that there's no heat interfering with the data, the image itself. It cools it down to about minus 30 degrees Celsius. And in front of the camera, we have a filter wheel. And here's one of the filters that we see. And we take individual snapshots through individual filters so that we don't have to interpolate. We don't have this interpolating between one pixel is this color, another pixel is that. All of the pixels are going to be of one color at a time, and we take multiple images to reconstruct a color picture. Here's an object that I photographed with a telescope in Australia called Centaurus A, which is a galaxy. Over here, this isn't exactly how it looked, but these are 4 individual frames that kind of representative of what the eye would see. These would be like the rods. This is just the luminance. There's no filter in front of the camera. And that's what this image is. These I've colorized. They really don't look like this, but these are with the red filter in front of the camera, with a green filter in front and a blue filter in front. You can see they don't look the same. They're similar, but not the same. They all are monochrome. I've colorized those myself just for clarity so that you can see which is which. And these images are combined into making a true color image. This is roughly what it would look like if you were close enough to be able to get enough light to see what color this object looked like. It would look like this, more or less. So the filters we use to get essentially true color are red, green, and blue. It's kind of reflective of what our eye does. And this is a graph of the transmission of a typical red filter, a green filter, and a blue filter. So this is wavelength and how much light it lets through. And in 1995, where there was a fundamental shift in palettes, when a seminal image was published by the Hubble Space Telescope that we're going to see in a little bit, called the Pillars of Creation. It did not use these colors, these color filters to create that seminal image, which we're going to see in a second. It used narrowband filters that were very specific and very, very different. It used a ionized sulfur filter. So this little sliver here in the far red, this hydrogen line, again, it's pretty red, very narrow, and double ionized oxygen, which is more in the green. And what was done was, instead of the channels in the image creation software were remapped so that the red channel, the sulfur, the ionized sulfur image was put into it. Hydrogen alpha, the hydrogen image was put into the green filter, and oxygen was put into the blue filter. Now, oxygen is not blue, and hydrogen is certainly not green, but that is the palette that was used, and it was done for a specific reason. So the reason that those were selected was because of the nature of how elements and atoms and molecules emit light when they're energized, or when they are obstructing. So in a normally heated object, it emits, depending on how hot it is, a continuous white spectrum of light called blackbody radiation. But when you energize something like hydrogen, the most common element that we have in the visible universe, it emits in very, very narrow bands of light, the most common being this very deep red in that H alpha, very tiny. When it's energized either by heating or by strong magnetic fields, it is bright in these colors and dominated by red. Conversely, it can also absorb light. It can reduce what we see by absorbing light. So for example, if you had a cool hydrogen cloud and behind it one of these light sources, the light coming at you would be absorbed by the hydrogen and then re-emitted. But the problem is when it's re-emitted, it's not going to re-emit that same light back at you. It's going to re-emit it in all directions. So you're going to get a significant loss of light that you receive. And so you'll get darkening in that part of the spectrum. That's called an absorption line. So this is an emission line. That's an absorption line. And here, these are the spectra of that sulfur, hydrogen, and oxygen that I mentioned. And here they are again, just plotted out. There's a few other extraneous filters on here. Here's that ionized sulfur, hydrogen, double ionized oxygen. So we can isolate those elements in something like the Pillars of Creation image. This is in the Eagle Nebula, and you can see on the right here, most of you should recognize this is a very profound image that was released in 1995. This is a star forming region with these big gas and dust towers being an incubator for brand new star formation. Well, if you look at that in what I'm calling true color or natural light, here's an image, the same image through the Webb Space Telescope using an RGB, and what you see is it's totally dominated by the hydrogen gas. It just overwhelms everything because that's what it mostly is. But the problem is, if you want to see information that's important, like ionized oxygen, double ionized oxygen, and sulfur, which are important parts of the process of star formation, by changing this palette to what's called the HST palette or Hubble Space Telescope palette, remapping into RGB these three narrowband filters, you get an image that looks like this, where you can see the oxygen here in the blue and the green hydrogen and the sulfur and the red in these clouds. So it's revealing a lot more information than you otherwise could see. But it doesn't look natural either. Again, this is what it's going to look like if you were close enough to the object to see it with your own peepers, kind of a thing. Not that. But this is revealing. It's incredibly revealing. Here's another example. This is not with the Space Telescope, but with an RGB palette and with the Hubble palette of an object called the Rosetta Nebula, which is also a star-forming region. Again, in natural color, as I'm calling it, or true color, it's just dominated by hydrogen because that's what it mostly is, and blots out most of the other information from this image. But when you use, instead of an RGB palette, a hydrogen alpha filter, an oxygen 2 or 3 filter, and a sulfur filter, you can see the individual components here, and when it's reassembled, it reveals much more information about what's going on. You can see the blues of the oxygen in here, the sulfur, and again, the hydrogen really being dominant. Now, one thing I want to mention is that this is more for presentation. It's not useless scientifically. It's very useful to combine and create an image like this. But the fact is, when scientists look at this information, they're really looking at this information, the monochrome images. If you want to look at where the ionized oxygen is, you wouldn't really look at this too much. You'd look at the O3 image in monochrome, and you can see exactly where it is, because that's all that is. There's nothing else in there. So the images, I'm just like anybody else. I want to see these great images, these overwhelmingly cool images that come out of the Webb program and out of the Hubble program. But there is a part of it that is just, creating an overwhelming image, or that is just so, I don't know how to describe it other than it's just grand. It's glorious, and the science itself is done in a much different level, where the scientists are actually looking at the individual pieces. So I don't know if I'm explaining that very well. Maybe Ed can provide some color on that later. Now, the good news is most of the light that we see, most of the electromagnetic light radiation that we get is from the sun, and we can see a good chunk of it. You can see here's a graph of the wavelength versus the irradiance, how much light there is coming from the sun. And you can see this is the visible spectrum here, and we're right at the heart of it. The sun emits more invisible light in the visible than any other part of the spectrum. And we're pushing, that's a pretty big percentage that we're seeing. Bad news is that we're missing a lot of information in the infrared where we can't see visibly at all. So all of these photons here in the longer wavelengths, we can't see with our eye. And on the other side, on the short wavelengths, in the UV and the X-ray and gamma ray, there's also information. There are photons that we cannot see. And I'll mention one other thing too, and that is light is where we get essentially all the information we have about the universe outside of our own immediate existence, we have from light. Light is the source of data that we have for understanding most of what we understand about the universe. So what range of light can we see? Well, we can see from 380 nanometers to 700 nanometers. And if we put up the electromagnetic spectrum in its entirety, here you've got the short wavelength, gamma rays, X-rays, ultraviolet. This little tiny sliver here is visible light that we can see. And then you've got the long wavelength, infrared, microwave, and radio waves. The Hubble Space Telescope was kind of centered on visible light, but it also could see somewhat slightly into the infrared and into the ultraviolet. The James Webb Space Telescope, for all practical purposes, is an infrared instrument. It can just barely touch into the visible, but it is designed to be an infrared telescope, going from 600 nanometers. Again, 700 is the cutoff to what we can see, going up to 28,000 nanometers. One thing I want to mention is that not all of the spectrum is available to us on the Earth. This here again is the spectrum of light from very short wavelength gamma rays to visible to very long wavelength infrared, microwave, and radio. And this shows how much of these different spectrum get through the atmosphere to the ground. Most of the radio and microwave does. Of course, the visible light does that we see. But none of the very short wavelength light, the high energy sources of light, of radiation, gets through the atmosphere, fortunately for us, or it would damage us. So X-rays and gamma rays and ultraviolet light are filtered out by the atmosphere. But so are infrared. Much of the area that the Webb telescope is looking at is filtered out by the atmosphere and doesn't penetrate to the surface. So you have to do these parts of the spectrum in space to be able to even collect the light that you're trying to study. So I want to show you something in multiple wavelengths and how different information emerges from looking at different wavelengths of light. This is a whirlpool galaxy. It's a relatively close galaxy. This was taken by Wayne State. This one is in RGB also. You see two galaxies colliding. This is kind of the fate of our galaxy. Our galaxy and Andromeda are headed right towards each other, and is going to look like this long time from now, but they are going to collide. Now here's what the Whirlpool Galaxy looks like in different wavelengths, and you can see just quickly, just by glancing, they look very differently in different parts of the spectrum. Here's the visible light that we saw. In the infrared, you're seeing cooler stars that make up the majority of the galaxy. The reason that, and in the ultraviolet, you are seeing younger stars that are much hotter and much brighter in the ultraviolet. In terms of why that is, older stars are basically red, they're lower mass, they evolve much slower than blue stars, and they're much cooler. They're more red in color, and large blue stars, they evolve 100 times faster. And so what you end up with are galaxies that are really dominated more by these much slower evolving red stars. But you can see the contrast, the difference between these two images. Here on the radio wave, you can see cooler gases and carbon dioxide molecules. I want to say one thing about, I don't want to spend too much time on this, but this is certainly false color. We can't see radio waves. The difference in colors are really, it's not a change in frequency that you're seeing, it's a intensity level. So the dark purple here are weak emitters, and the closer you get to red, you get stronger and stronger radio emission in the same frequency. And then over in the X-ray, you've got extremely hot gases near the core that are 10 million degrees. And these individual dots that you see here are the result of the most energetic phenomenon in our galaxy, neutron stars, black holes, pulling in matter, things like that. Here is another one to look at. This is the Crab Nebula. This is a supernova remnant. This was an image from the Zowada Observatory taken. These were all during the test phase, by the way, of the observatory in RGB. And in 1054, there was a supernova, a star exploded, was recorded by the Chinese. And this is what's left over from it, matter being spewed out from this explosion. And at the very center is a neutron star, very dense star, very powerful magnetic fields, and spinning very fast, about 60 times a second. It's an amazing object. Here's that object in different wavelengths. So in the optical, we see the filaments of the hydrogen that being blown off of the outer atmosphere of the star. The radio waves are from incredibly powerful magnetic fields, creating synchrotron radio emission. The infrared are the gas that's being heated by the surrounding plasma and neutron star. And in the X-ray, very different image. These are showing basically gas nearby that are being powerfully heated by very strong magnetic fields to extremely high temperatures, 10 million degrees plus. You can also see matter being ejected from the poles of the spinning neutron star. But put it all together, and you see a very fascinating composite image of the Crab Nebula represented in these different frequencies of or wavelengths of light. So as I mentioned, the Webb telescope is an infrared imaging spectrographic system. And here's wavelength now in microns. Here's visible light over here. The bulk of the observations will be done in the near infrared with the near infrared camera. It, as we pointed out, it goes all the way out to almost 28,000 nanometers, or 28 microns. So what's so special about infrared light? Well, there's three things that I'm going to mention. There's more than these. And I would refer you to Dr. Ed Cackett's talk. He gave a fascinating talk that is online that you can watch that talks about really the mission objectives, the science objectives of Webb. It's fascinating that I encourage you to go and look at. But here are three reasons that I would give. First is that the earliest stars and galaxies in the universe are shifted into the infrared. They're not even visible in visible light, or that the majority of their light that is produced, that we receive, is in the infrared. We'll explain that in a second. So we're able to see very far back in time at the earliest stars and galaxies. The second reason infrared is critical is that stars and planets being formed are in our own galaxy that are close to us are obscured by dust and gas, and so we can peer through that and see what's going on. And a third reason, of more than three, is that molecules needed for life, at least as we understand life on Earth, are detectable in the infrared. Let's look at the first instance. The early universe. So as we peer further and further out into space, it's literally a time machine. We're looking back in time further and further and further. And that's because light has a fixed speed. And so light that we receive from the sun is only a few minutes old. So we're looking at a relatively current version of the sun. But if you look out to a galaxy, it might be 1 million light years away. It might have taken 1 million years for the light that we're seeing from a nearby galaxy. That's a close galaxy. It took it 1 million years for us to even see it. And so the further back we look, the further out we look into space, the further back in time we're going. And so this graph here shows the Hubble telescope and the Webb telescope in terms of how far back in the past it can see. And you can see this is the Hubble limit here. It doesn't have the ability to go further because of its size and because it doesn't have infrared sensitivity. The Webb telescope is both much bigger and sensitive to infrared light. So it can go back much, much further into space, which means much further back into time, to see these very red objects. Red is an infrared. Out to the point of even the first formations of galaxies and stars, that far back, which is mind-blowing to think about that. Now, why is it so red? Well, it's so red because the universe is expanding rapidly. It started from essentially a small point, and it expanded quickly, and it continues to expand to this day. And we have something called the Doppler effect that shifts light. The faster something is moving towards you or away from you, the more that the light is shifted. And the Doppler effect can be seen in everyday life in sound waves. If you were watching a race car come towards you, you know that the pitch is very high. And when it passes you and moves away from you, the pitch drops very low. So you'll see the car coming. It's the same sound, but when the car's coming towards you, the waves are compressed. You're seeing the peaks quicker, so the frequency is higher and it sounds higher. It's shifting to a higher frequency. And when it moves away from you, the pitch drops because the sound waves are being elongated. The same thing happens to light waves, whether they're coming towards you or away from you. And when we want to look at the early universe, we're talking about light that is incredibly shifted towards the red by a factor of 10 in the spectrum. And so if we want to look at the earliest galaxies, they're moving so fast away from us that all the light that really should be ultraviolet. It starts out in the ultraviolet here when it's emitted, winds up in the ultraviolet when we receive it 13 billion years later. So this is why it's so essential to be able to see in the infrared, to be able to detect these. Now, this is a point of personal privilege just to blow your mind. If you can't do that as in talking about astronomy, then why talk about it? But the size of the universe is just incredible. And I wanted to reflect on the Big Bang for a second here, and that is, I think we have an intuitive understanding of how big the Earth is. It's enormous. It's gargantuan compared to the city of Detroit. But think of this, that you can fit over a million Earths could fit into the sun, our own sun, a million of them. That's just incomprehensible. And think about this, that our sun is just one of 150 billion stars in our own galaxy. 150 billion suns in our own galaxy, stars. And those galaxies make, our galaxy makes up what we currently can observe as 200 billion galaxies in the observable universe. It's just, you just can't, very quickly, you lose the ability to even comprehend the size. And I found a model online. It's amazing what you can find online. I found a model of the early universe that I wanted to show you. I ordered it a few days ago and got it. This is it. This is a model of the early universe, right after the Big Bang. This doesn't look terribly accurate except for one thing. This is to scale. This is the size of the entire universe at one time. Now think about that. Everything that I just put up, all the matter, all the dark matter and energy that we didn't even talk about, everything was contained in that small sphere at one point in time. It just blows your mind. So, so Webb has already released what we call a deep field image. And this is an image where it's staring at essentially an empty part in space, doing a long exposure to try and see very deep, very distant out into the universe. This is a 12.5-hour exposure. And I can't give you a lot of detail because it just came out. Maybe Dr. Kaka could talk about the deep field. But you can see the bizarre nature of these early galaxies and how, well, what the thing that to remember is all of this is infrared light that we're seeing, all of it. It's all shifted down into the visible light so that we can see it. So nothing that you're seeing here is really white or blue. It's rendered that way by taking different segments of the infrared from the longer wavelength infrared to medium to the long wave infrared in the spectrum that it sees to construct this false color image that it's seeing. But be assured that these are all very deeply red objects except for this star. And in fact, a lot of the research is going to be done. The furthest galaxies out might just simply be pinpoints. We still can't, they're so far away that we can't see structure, but we can measure in composite a point source to be able to study these early objects in the universe. Okay. So the second point that I put down was that new stars are obstructed by dust and gas. Here's a very cool site that I have a link to at the end of my talk of USpace that the Space Telescope Science Institute manages. It's fascinating. But here's an example, a real life example of how this works. And here is a smoke-filled room that a fireman is in. And we really, the light, the visible light is being scattered, and any detail in there is being obscured because the visible light is being scattered to the point that we can't see anything. However, in looking in the infrared, you can see very important detail. The red light, the infrared light is able to penetrate that gas, the dust and the soot and the vapor, and we can see the person laying on the ground. This is an actor. You can see clearly the outline of the person. You can see the cool tank, the oxygen tank that the firefighter has, and the hot exhaust of their breath going through the filter and so on. So critical information can be seen in infrared light that is invisible to us. So similarly, here's a picture of the Lagoon Nebula, which is a star-forming region. Stars are being born here. And this is invisible light using the HST palette, the Hubble Space Telescope palette. So this is showing oxygen, sulfur, hydrogen. But we really can't see through the cloud. We can see the cloud in detail about it. But when we peer at it, and this is just the infrared that the Hubble, the bit of infrared that Hubble sees, you can see, we can pierce right through it. We can see stars in the background, and we can start to see the stars that are being formed in this region. Hubble will, the Webb telescope is designed to be able to pierce through and show us the mysteries of what is going on in these star chambers, these star birthing chambers. So exoplanet research is another important piece of research that the Webb will be doing. An exoplanet, we are planets that are orbiting stars. We actually don't see the planets; they're too small to resolve, even with the largest telescopes. But we see the remnants, or we see tracers of them by measuring light. So here is an exoplanet, a planet orbiting a star. This is kind of an overhead view where a telescope is looking at it. And when the star passes in front, when the planet, passes in front of the star, there is a drop in the apparent brightness of what we're measuring. So we can see the effect of a planet basically casting a shadow or just blocking the light from the star that it's orbiting. And we get a characteristic light curve like this. Now, Webb will not be really exploring for exoplanets, but following up on observations of other missions that are specifically designed to look for exoplanets, to look for the ingredients of life on other planets. They've already released a result. Very exciting. This is the WASP 96b atmospheric composition. And when this planet passes in front of the star, some of the light goes through the atmosphere of that planet. And you can look for signatures of things like water vapor, which was found in this WASP 96b candidate here in the infrared spectrum. So here's the wavelength and here's the absorption. And I don't know how well you can see this, but you can see that you can see the water detected in the models that they have for the light passing through. So in the infrared, as I mentioned, that signatures of life, as we understand it, can be looked for like methane, water, molecular oxygen, ozone, carbon dioxide. All of these can be detected. These are detectable in the infrared by the Webb telescope, and a considerable amount of its work is going to be exploring these exoplanets to see if there are Earth-like planets out there, and potentially planets that can host life. Throw this in real quick too. Actually, the observatory, the Zowada Observatory, actually detected one of these exoplanets, Qatar 2b. Dr. Cackett sent me this beautiful light curve showing that phenomenon of the planet eclipsing passing in front of the star and the light dropping. And I was very excited when I saw that. The instrument was that sensitive. And I would finish with the investigation of protoplanets and how planets are formed in our own galaxy. This is a very nearby object, relatively speaking. This is a radio image from the ALMA telescope of, what is it? That's HLTAR. And here we have the young red star, and we have all of this disk material around it where planet formation rather is thought to occur. Webb will be so sensitive that it'll be able to look through these bands and be able to detect organic materials like methane, all these different hydrogen cyanide, ammonia, carbon dioxide, and so on from the spectrum of the star. Now, a lot of the search for these organic materials, these different signatures in early planetary systems aren't going to have the benefit of being able to see a disk where you can actually see them. They'll just be point sources because they're too far away to resolve like this. But they'll still be able to make the same measurements to see if these materials are in the atmospheres of the planets. So you can see that astronomy and the universe, our understanding, comes from a wide range of electromagnetic radiation, from gamma rays to all the way through radio waves and everything in between. And that the science is done throughout the entire electromagnetic spectrum in space and on the ground. And that we're going to be seeing an awful lot of just mind-boggling results coming out of the Webb telescope over the next few years. It's going to dominate a lot of the astronomical findings. But it'll also complement and be complemented by many of the other wavelengths and observatories around the world. Okay, here's some cool links that I encourage you to check out. I went a little longer than I had intended, which I apologize. And thank you for having me.
Great, that's okay. We're good on time. Thanks so much, Russ.
Thank you, Russ. Yes, I don't know whether my brain could have taken 2.5 hours. It was great.
We've had several questions coming up in the chat, and I would say if anyone else has questions, feel free to put them in there. And I will try to get them out to Russ as best as, sometimes I catch them late and then I'm not sure what they refer to. So if I mess up your question, just tell me. One of the questions we had from AC was saying, since hydrogen is the most abundant elements in the universe, doesn't it mean that all visible light from other than stars is emitted as red biased? So are there other biases because of all the hydrogen to what you're seeing?
No, not really. In the gas forming regions, but hydrogen gas collapses, in stars. And so like in a blue star, all that matter collapses into a much hotter entity, and a much different type of light is emitted. So not really. It just depends on the source.
Thanks. When we receive infrared from JWST, how do we know precisely which stars or galaxies the light is coming from?
Well, a lot of them are new that we've never seen before, for one thing. Well, from other wavelengths for stars where we can see, there's many objects that's going to be looking at where we have a lot of information, like the Lagoon Nebula. It's nearby, it's large. Amateur astronomers have photographed it for decades. And so many of the objects are like that. But further out, faint objects, especially ones that have never been seen before, they're brand new discoveries. And so you've got everything in between, from never seen objects, which hopefully we'll get a lot of as we peer into the early universe that we've never seen before, to objects that have been heavily studied for many, many decades.
Another question came up related to both gravitational lensing and micro lensing. The question was two questions. One was about asking if gravitational lensing is responsible for the distortion of galaxies in the images from JWST in the deep field. And then someone else was also asking if micro lensing was involved with some of the information you had about the exoplanets and how we were seeing the exoplanets.
That I can't answer, but the answer is yes. Gravitational lensing was part of the first image they released. You could see it, and you can get a sense of that from looking at the distortion of the image from that. I can't answer that about the exoplanets. I don't think so, but Dr. Keka might be able to answer that question.
Okay, we may.
Yeah, I can answer that. So microlensing is not involved in that transit stuff. So as the planet transits in front of the star, it just blocks some of the light. Microlensing is a little different. So that works when we have one star passing in front of another star, and the gravity of that star acts like a gravitational lens. You see a little blip in the brightness, and you can also detect planets that way. So that's a different way of detecting planets. It's a little different than the transit stuff that Russ was showing.
Awesome, thank you. My next question, I don't know which of you will want to take this one, was will JWST change the value of the Hubble constant? And maybe explain what the Hubble constant is when you do that for folks who are unfamiliar.
That's an Ed question.
That's what I thought.
So the Hubble constant is a measure of the rate of expansion of the universe. And there's actually, it's a really, people have been trying to measure it since we discovered, or Hubble discovered, that the universe was expanding back in the 1920s. And
We just started the questions.
as we get closer, and the value has been getting more and more accurate, and it's become a really hot topic, trying to figure out exactly what that value is. The measurements from the current day are different between different methods. So people are trying to actually figure out what's the actual value of the Hubble constant still. There are different ways of doing this, and Webb will be able to do this, particularly with supernovae. And there are several other different techniques that Webb can use. And there are a whole bunch of other experiments taking place over the next decade that are all trying to answer or clarify this question of what the Hubble constant actually is.
Awesome. The next question is about the telescope, particularly how is the telescope staying at the L2 Lagrange point and staying in orbit with the Earth when it's 1 million miles away from us?
You want to take that, Ed?
Sure. So the Lagrangian point is basically this really special place in the Sun-Earth gravity system. So there are several points where the gravity and other forces balance just right, that it's what's called an unstable equilibrium point. So the telescope can stay there with using very, very little fuel, which means it's a really special place. We've put several telescopes there before because it's a really cool place. The great thing is that it means that if it's there, it actually tracks the Earth. It also takes only 1 year to go around the sun. So it always stays in the same position relative to the Earth, pretty much. So it can stay there with little fuel. Because it's 1 million miles away, it means it's colder and darker. And so it's a great place to do infrared astronomy, where thermal radiation can be a problem. Yeah, it's a really special gravitational point, and that's why they chose to put it there.
I found a nice link on the website that I put in the chat too that talks a little bit more about that and the other Lagrange points too for people who want to deep dive. The next question I have is more about just, I thought this was a fun one, not about Webb specifically, but are there any telescopes at the South Pole that can observe UV light because of the ozone hole? Wah, wah.
I don't think so.
Yeah.
No.
There
I
are
know there-
telescopes at the South Pole.
There are telescopes, but I don't think they look in the UV.
Yeah, there's no UV telescopes on the ground. We often send up balloons from the South Pole or from from the Arctic or Antarctic Circle as well, because you can if you can send a balloon up, the balloon can get high enough above the atmosphere to be able to look in the ultraviolet or in the X-rays, and that's how a lot of that actually early X-ray astronomy was done, from either little rockets or from balloons.
Yeah, and I would also, sounding rockets I was going to mention, but also there's a nice instrument called SOFIA, which is an aircraft that flies an infrared telescope into frequencies that you can see from these high altitude airplane level altitudes, that has done some very, very important work in the infrared. But it is limited.
I think that is every question that I saw, but please let me know, Jennifer, if you think I missed any.
I didn't see any that you missed, but if anyone has a question that you'd like to get in, please ask it now. Megan very kindly put in the link to the YouTube channel. This recording will be on the YouTube channel in a few weeks.
Okay.
We try to have programs on the 4th Tuesday of the month. We're not trying any for August. We do have a program. We're working on the program for September, but that's not finished yet. But we do have the programs for October and November. Mark Christensen had a comment about SOFIA.
Yeah,
it's-
Mark. Oh, go ahead. Sorry, Russ.
I was going to say, yeah, it's being mothballed. Unfortunately, it's near the end of its life, and it's being repaired apparently right now in New Zealand after some storm damage. But it is on its way out. It's very expensive to operate. It's a 747. It's not too carbon friendly on top of that. But it is an amazing mission. It's done some amazing research.
Do you know when it started? How long it's been going for?
It's been around for quite a while.
Yeah.
I'm blank, but it's been around for a while. It's at least 10 years.
Okay.
Yeah.
All right. Well, thank you everyone for joining us. Thank you, Russ.
Thank
This
you
was
for having me.
mind-blowing.
Really appreciate it.
I knew bits of it, but you explained it very, very well.
Mhm.
Thank you. And
Thank
we're very
you. And
lucky
thank
to
you,
have-
Megan. I always appreciate your help. Thank
You
you,
too,
Ed,
Jennifer.
for being willing to be dragged in to answer more questions.
Yeah, and thanks, Dr. Cackett, for jumping in too. It's nice to have an astrophysicist on hand.
I have an astrophysicist in my pocket and I'm not afraid to use him. Okay, thank you, everyone.
Alrighty.
Goodbye.
Bye-bye.